We have studied that there are two types of DC machines, DC generators and motors. These machines convert one form of energy into another form. Now, during this energy conversion, some amount of power is wasted in the form of heat. Now, these losses occur in different parts of DC machines, and all these losses cause heating of machine. Now, this heat generated by these losses has two major serious effects. The first effect is because of increase in temperature of machine, the performance as well as life of the machine gets affected. Particularly, life of insulation depends on the temperature rise, and therefore the rating of machine is directly affected by these losses. The second important effect is reduction in efficiency because of wastage of power, and therefore because of wastage of power the operating cost or running cost of the machine increases. Now, this increase in operating cost is mainly important in case of large machines where large amount of power is required. However, temperature rise is very important in case of large as well as small machines because temperature rise directly affects the performance and life of the machine. Now here you have to note that these losses cannot be eliminated completely, but we can reduce the losses by proper design of machine, and we can increase the efficiency of machine. But naturally, efficient machine will be more costly, and therefore the initial cost of machine is greatly affected by these losses. So therefore, losses directly affect the rating of machine as well as cost of machine. And therefore, it is very important to study these losses in detail and to study how to reduce these losses so as to increase the efficiency. So in this video, we will study various types of losses that are taking place in DC machines. Various types of losses that are taking place in DC machines can be subdivided as first is electrical or copper losses. Second is magnetic losses, which are also called as iron or core losses. Third is mechanical losses, that is friction and windage losses. And fourth is stray losses. Let us now study all these four losses in detail. First type of losses in DC machine are electrical losses. These losses occur in the windings, that is armature winding and field winding, because of the flow of current through them. Now, when a current of I ampere flows through a winding of resistance R ohm, then the amount of power wasted in the form of heat is I square into R, and that's why these losses are also called as I square R losses. Now, as it is taking place in the winding, which is normally made up of copper, these losses are also known as copper losses, winding losses, or ohmic losses. There are three types of electrical losses. The first is armature copper loss, which is equal to Ia square into Ra. Here, Ia is the current flowing through armature and Ra is the resistance of armature including the resistance of interpole and compensating winding. Now, when the machine is loaded, the current through armature will change, and therefore this loss is a variable loss and it depends on the load on the machine. So, as the machine is loaded, the current in armature Ia will increase and armature copper loss will increase according to Ia square, and that's why this loss is a variable loss. Now the second loss is field copper loss. Now you know that there are two types of field windings, shunt winding and series windings. So in case of shunt generators, the copper loss, it is equal to ISH square into RSH, where ISH is the current in shunt field winding and RSH is resistance of shunt field winding, or it is also equal to V into ISH. Now as the shunt winding is connected in parallel with armature, current through field winding ISH is almost constant, and therefore the field copper loss which occurs in shunt field winding is practically constant. In case of series generator, the current in series field winding is ISE and it flows through resistance RSE, and that's why the copper loss taking place in series winding is ISE square into RSE. Now when the load on machine increases, ISE will increase and the copper loss in series field winding will also increase, and therefore this loss is not constant, it is variable and it varies according to load on the machine. Now the third type of copper loss is the loss due to brush contact resistance, but normally this loss it is included in the armature copper loss. Second type of losses in DC machines are magnetic or iron or core losses. These losses include hysteresis loss and eddy current loss. Let us first see what is hysteresis loss. Now in DC machines, armature is rotating under the field poles. Now when the armature core passes through one pair of poles, that is one north and one south pole, it undergoes one complete cycle of magnetic reversal. Means, first of all, the core will be completely magnetized, then demagnetized, and then magnetized in reverse direction. Now, in this magnetization and demagnetization, you can see that at every instant, the flux density B is lagging behind magnetic field strength H. This lagging of B behind H, it is called as hysteresis, and this loop formed because of this hysteresis, it is called as hysteresis loop. So because of this continuous magnetization and demagnetization, that is magnetization and reversal of magnetization, the core gets heated and the energy is wasted in the form of heat. So this loss of power because of this hysteresis, we call it as hysteresis loss. And this hysteresis loss depends on the area of hysteresis loop. Now this hysteresis loss is given by Steinmetz formula, and it is given by WH is equal to KH Bm raised to 1.6 F into V watts, where KH is Steinmetz hysteresis coefficient. It depends on nature or quality of the magnetic material used. Then Bm is the maximum flux density in Weber per meter square. F is the frequency of magnetic reversal in hertz or in cycles per second, and V is the volume of core in meter cube. So you can see that hysteresis loss depends on Bm, and it depends on the applied voltage or the current through the field winding, and it also depends on F, that is the frequency of reversal of magnetization. So this F depends on speed of the machine. The second type of core loss is eddy current loss. In case of DC machine, armature core rotates in the magnetic field produced by field poles. So when it rotates, it cuts the magnetic flux. And therefore, according to Faraday's law of electromagnetic induction, an EMF is induced in the core. So this induced EMF circulates a current in the core, and this current flows in the circular paths, and that's why, because of this particular shape of current, this current is known as eddy current. Now when eddy current flows through the core, then because of current flowing through a resistance, there is loss of power, and some power is wasted in the form of heat, and this loss of power because of eddy current is known as eddy current loss. Now in this case, as the core is solid, its resistance is very low, and therefore eddy current will be very high, and therefore eddy current loss is also very high, and the core will get heated. And to reduce this eddy current loss, instead of using solid core, we use a laminated core. So in case of laminated core, the core is made up of thin laminations. So thickness of laminations is about 0.3 to 0.5 millimeter, and each lamination is insulated from each other by a thin coating of varnish. So because of this, the resistance of core increases and eddy current decreases, and it will also reduce the eddy current loss, and heating of core will also reduce. Let us now see the expression for eddy current loss. So it is given by We is equal to Ke Bm square F square T square into V watts, where Ke is a constant which depends on nature or quality of the magnetic material used. Bm is maximum flux density in Weber per meter square. F is frequency of magnetic reversal in cycles per second. T is thickness of lamination in meter, and V is volume of the core in meter cube. So here eddy current loss, it depends on maximum flux density and frequency of magnetic reversal, and it varies according to F square, and it is also proportional to Bm square, which depends on applied voltage V, and that's why it is also proportional to V square, and it also depends on the thickness of laminations used. Now, in order to reduce iron losses, that is hysteresis and eddy current losses, special silicon steels are normally used in case of DC machines. Now, these steels have a low hysteresis coefficient which reduces the hysteresis loss, and these silicon steels have high electrical resistivity, and therefore eddy current loss is also reduced. Third type of losses in DC machines are mechanical losses. These losses include friction and windage losses. Windage losses are the losses because of friction of rotating parts with air, and therefore friction and windage losses are caused because of rotation of machine, and that's why these losses depends on the speed of the machine. Now, the frictional loss, it depends on the type of bearings used and also on the viscosity of the lubricant. Then another major part of frictional loss is brush friction loss. It depends on the contact area between commutator and brushes, and it also depends on brush pressure. Then the other factors on which brush friction loss depends are the material used for brushes and commutator, and it also depends on their polish conditions, that is polish condition of brushes and commutator. Then windage losses, these are caused because of the air moving around the rotating part, that is armature. Then ventilation loss is also a part of windage loss. So for cooling of machine, we have to provide a fan, and this fan also consumes some power, which is also a wastage of power. So this ventilation loss because of this cooling fan or because of these cooling ducts, so it is included in the windage losses. Now, next type of losses in DC machines are stray losses. Now, there are some losses in the machines which cannot be considered as previous three losses, that is, as electrical, magnetic, or mechanical losses. So, such type of losses, these are called as stray losses. Now, these stray losses are very small in value, and therefore these are very difficult to calculate. And that's why in case of small machines, stray losses are generally neglected. In case of large machines, stray losses are considerable, and therefore normally these losses are taken as 1% of the total output power. Some examples of stray power losses are additional core loss because of distortion of flux due to armature reaction, or copper loss due to short-circuited coil during commutation, or copper loss due to non-uniform distribution of current in armature conductors. So these losses are very difficult to calculate, and these cannot be considered in electrical, magnetic, or mechanical losses, and that's why these are called as stray losses. Some losses remain constant with change in load, whereas some losses vary with change in load, and therefore some losses are constant and some losses are variable. So the losses which remain constant irrespective of the load conditions, these are constant losses. Now the mechanical losses, core losses and shunt field winding copper losses, these are practically constant from no load to full load, and therefore these are included in constant losses. Whereas some losses depend on load conditions. So when load is increased, these losses will also increase. These are variable losses. So armature copper loss, series field winding copper loss, the loss of power taking place in interpole and compensating winding, and brush contact power loss. So these losses are included in variable losses. Now before stopping, let us summarize what we have studied. So we have seen that there are four types of losses: copper losses, iron losses, mechanical losses and stray losses. So copper losses are taking place in the winding, that is armature winding and field winding. So it includes armature copper loss, interpole and compensating winding copper loss and brush contact resistance copper loss. So all these losses are variable. Then series field winding copper loss, it is also variable, and loss of power taking place in shunt field winding. And as shunt field winding current is almost constant, this loss is practically constant. Then iron losses are taking place in the core, and these are hysteresis losses and eddy current losses. These losses are also practically constant. Then mechanical losses, these are because of friction and windage loss, and these are also constant. And there are some losses which are very difficult to determine and which cannot be included in copper, iron or mechanical losses. These are stray losses. In our next video, we will study power stages and efficiency of DC machines. Thank you.